All right, so in the second portion of the lecture video, I want to go over EDS, or Energy Dispersive X-ray Spectroscopy, and this is done in an SEM, or Scanning Electron Microscope. So I'm just going to go very quickly over the basics. The main thing I want to introduce in this is what we're going to use the EDS for, and what that gives us and what it can tell. So I won't give a huge background on the instrument, SEM or EDS, but I want to show you what we can get out of this technique for our lab. Okay, so just very basically, in SEM, we have an electron beam, kind of shown here, and we focus that to our sample, right? So in this case, this would be our glass sample. And it interacts with that sample in a given volume. So you see the interaction volume down there. So it's not just a point. It's actually a volume into the material, depth, and it spreads out a little bit as well. And from there, the EDS aspect of the machine is a separate detector. And so what that's doing is it's detecting X-rays that are produced from the surface, so from the sample itself. So this isn't part of the instrumentation to image, it's kind of a separate entity. And so if you're wondering why there's X-rays, well, what happens is in our sample, there's going to be an atom, right? We're just looking at one atom here, but the incoming or incident electrons come in, and those electrons are at really high energies. And if they can interact with an electron in your atom, they can actually knock it out, and they can eject an electron from an atom. In doing so, another electron from within the atoms is going to come down to this inner shell that we have, because it wants to get to the lowest state possible, right? The ground state. And so a higher energy electron will move down into that inner electron spot. And in doing so, because the energy of electrons is quantized, the difference in energy between these two spots will produce energy, and it does so in the form of an X-ray, because that's the right energy and the right wavelength. And that X-ray will have a very specific amount of energy or wavelength. And that's going to be tied to the difference in electron energies here, and this will be tied to what type of atom we have. So if this is copper or carbon or whatever it is, will depend on what the energy value is. So we're basically going to detect these X-rays and measure their energy, which will allow us to determine what elements we have in our sample. So that's what we're going to do. So again, this is just kind of showing the same aspect here. And so different transitions will give us different energy values, which we can then tie back to a specific element. And so this is what we typically get, the results we typically get from a certain spot. So we look at, so basically this is energy, and then this is the intensity axis up here that's not shown. So what we see is we kind of see some background noise here, but then we see peaks, right? And these peaks represent the detection of an X-ray of specific energy, right? So this is 6.5 kilo electron volt. This is about 7. This one is 3.75, something like that, right? So these specific energy values will be tied to different elements, and different elements can have multiple peaks. For example, where do we have? So for iron, then we actually see what's called a K alpha and a K beta, and so we also see an L alpha down here too. So if we have an element, if we have iron in the sample, then we would have these different transitions which tie back to these different transition in the atom. And so we can use those different values as a fingerprint. And so if we see these 3 peaks together, we know that that's iron. And so the same thing with other values as well. If we see specific values, we can relate that back to an atom or to an element. So a couple things about EDS. So the relative strength of the signal can also be used to quantify how much, right? So you can see here that this is a pretty strong peak, whereas some of these others are low peaks, right? And so this tells us about, can tell us about quantification. A couple things about the sort of error and limitations. So EDS is not great at detecting very small amounts. And so the detection limit is about 0.1%. So there are other techniques out there if you need to know like trace level impurities, but this is not great for that. And also, in terms of quantification, our kind of standard error is about 1%. So we're not getting a super detailed amount of what elements we have in there. We're getting, again, plus or minus 1 or possibly even more in terms of the error when we talk about quantification. All right, so let's look at different ways in which we can perform this energy dispersive X-ray spectroscopy. So what we just saw as an example was a spectrum, the actual peaks for the characteristic X-rays. And that is done at a single point. So this is known as a spot or a point scan. And what we do here is we take the image with SEM, so we can see what we're doing, what the features are and so forth. And then we basically pick a point, a spot 1, for example, and we basically force the beam of the SEM, the electron beam, onto one spot, right? And so if we go back, it's basically we're forcing this electron beam just to a single spot on the sample. And keep in mind, these single spots are quite small. So, they're on the orders of nanometers. We're not talking large spots. And so that one spot, we hold that beam at that one spot and we detect the X-rays that come off. And so the X-rays that you see here are only coming from this spot and the interaction volume that it occupies. So that's one type of, we typically call this a spot or a point scan. So this is a very common way to look at something. We can also broaden it out a little bit. We can make some type of area. So a rectangle is very common in SEM. And so we can basically, in the software, choose to select an area. So this one's called Area 2. So we're looking at this area. And instead of holding the beam at one spot, we basically scan the beam, because it is scanning electron microscopy. So we can scan that electron beam across this whole area. And so we take the resulting characteristic X-rays from the entire region. And so we're basically averaging the spots in this area. So instead of one spot, we have a whole range of spots, and we're looking at basically the collective data from that area. And so this is the region from there. So this is if we want to get a wider region of analysis. So that's typically known as an area scan. And then lastly, in this slide at least, we have what's called a line scan. And so here, again, you take an image of the sample, and then what we do is we draw a line. And this line is then recorded. So essentially, instead of collecting all the data and just having one scan like we do here, what we actually do is we keep all the points separate. So there's hundreds of points along this line. And what we do is we collect data at each point and we keep it separate. So we have we have this basically curve at each point along the line. And then what we do is we plot that, and we plot that as a distance along the line. So you can see here that this is starting at 0, so up here, and then working across the sample over here is the other side. And so we look at the relative amounts of these peaks at the different points. So we keep all that data separate. And what that does from this line of points is it allows us to detect differences in composition along that line. So here you see that from 0 to a little less than 2, things look consistent, right? The composition of the different elements, so sulfur is up here, copper, copper, and then a couple other elements down here, they're pretty consistent in terms of the ratio. However, at about this point, the carbon, it looks like, goes up. Or sorry, that's molybdenum. And then that shoots up. So you can see that at that point, which is about right here, the composition changes, right? And so this is one of the most useful ones that we're going to see for our sample, because diffusion is occurring from the outside of the glass rod inward. And so we would expect compositional differences. And so we're going to use this linear form, the line scan, to get differences in the composition from the exterior of the glass to the interior. So this is going to be something that we look at for our samples, particularly the cross sections. All right, so let's look at one last way that we can interpret EDS data, and that is what's known as a map. So EDS mapping, or compositional mapping. So this is, again, an SEM image. So you see that there's kind of different contrast, but we don't know where that contrast is coming from. So what we do is we are basically going to do EDS on the entire region. But again, instead of averaging or compiling all the data, we're going to keep it all separate. And so at each point, at each spot in this, which has thousands or millions of spots, we're going to collect data. And so what happens is we're going to collect data for an iron peak, manganese, cerium, cobalt, etc. And if we see that element at a specific point, we're going to identify it, right? So here, the yellow spots indicate that we have detected iron. And the greater intensity we see that yellow means the greater intensity of iron. And then we're going to color code the next spot. Is if we see a manganese peak in that spot, we're going to color it green. And same thing, we're going to see that. And then we're going to keep color coding different EDS characteristic X-rays. And so that will allow us to map where we see particular elements. So it's like that line scan, but we're doing the line scan on the entire area, and we're sort of color coordinating each different element so that we can see what we have. And what that does is, again, allows us to see differences in composition. So we see that this middle region corresponds to iron, cobalt, and strontium down here. And then we see the top layer up here is manganese and nickel. And then we see the bottom region looks like it has some manganese, but mostly zirconium. And so we see differences, and then a little ceria. So we see differences in the composition, and we see it spatially, so along the space of the sample. Keep in mind these colorations are false colorings. And so if we have time, we're definitely going to try this to, again, see if we can detect differences between the exterior of the glass rod, where diffusion is the highest, and then towards the interior, where there will be less and less of the ion exchange happening. All right, so I want to look at a particular line scan that was actually done for some of our samples. And so this was a sample that was ion exchanged. So one of our soda lime or flint glass rods ion exchanged with a silver containing solution. And so here's the image. It's not super bright, but basically over here on the image, you see that's basically nothing. So it's the edge of the, so this is basically the edge of the glass. And then it's not perfectly flat, so you see a little bit of compositional, a little bit of contrast change here. So it probably had a fracture surface. And then this is the going towards the interior of the glass, and the arrow indicates the direction. So basically this is 0, and then this is going on into higher and higher numbers in distance. Oh, and it gives us the label here. So this is the line scan for silver nitrate, and it was actually exchanged for 48 hours. I don't know what temperature, but this is some previous year's data. So what we see is that, for this initial region, we don't really see any we don't get signal. So we're not getting characteristic X-rays because there's really nothing there. However, right around 20 is where everything starts, and so that's the edge of the glass. And if it's the edge of the glass, that's also where we would expect the highest concentration of the exchanged species. And sure enough, If you look over here, the red is silver. It's actually the L alpha peak. And so you see it peaks right at the basically beginning of the glass rod and then tapers off as we go into the glass. And then here you can kind of assume this is the background level of silver signal. And so basically this glass wouldn't expect to have any silver, and so this is basically 0. And then this is the highest concentration up here. Let's look at the other species. So we also looked at calcium. Calcium is in our glass to some extent. And you see that right when it starts, we get calcium signal, and then there's some error. There's some up and down, but that's basically just the error level of our instrument. So you see that calcium is more or less flat. So nothing really happened with calcium in the glass. However, let's look at sodium. So in sodium, again, 0 at the edge of the glass, and then it goes up. And what we actually see here with the sodium is that sodium has kind of a level down here, and then it actually appears to go up, right? And up to sort of a steady state value right here. And so this could be inferred as the concentration actually decreased for sodium near the edge, where the concentration of silver is the highest, right? So the basically silver concentration goes up and it's exchanged for sodium. And that's the exchange we expected when we discussed in the background. So that makes sense. We've tried this with potassium as well, but one thing with EDS that we see is that the signal for silver is the best. And this has to actually do with the element itself. Silver is a relatively heavy element, and so EDS works better for it. The collection efficiency of X-rays for silver and heavy elements is better, as opposed to potassium, which is relatively small. The collection efficiencies are pretty low. So even in our samples where we had substantial potassium exchange, we might not be able to see it on EDS because of the nature of the X-rays, not because potassium isn't exchanging. So that's one thing we have to keep in mind. We will do the analysis on that, but we may not be able to see it. Okay. So this is one type of scan, and again, like I said, we can use this. We can also use the EDS map, and so that's another technique we will try. Typically, we're not able to do this on every single sample because the collection here takes a long time because we have so many spots. So we'll mostly do line scans, but we will do some EDS mapping and some imaging to show you where we're getting this data from.